Okay, today's lesson is going to be on thermodynamics. Okay, it's a continuation of the last lesson we had. Okay, for today, our first equation to learn is this equation from the ideal gas equation, PV equals nRT. Okay, P is your usual pressure, V is your volume, N is your number of moles, R is a gas constant with the numeric value 8.31, Joule per Kelvin per mole is a unit, T in temperature of Kelvin. nRT is normally used rather than NKT. But if you're using NKT, N is actually the number of molecules. Okay, you actually take N to be equals to number of moles times the Avogadro's numbers of 6.02 times 1023. And again, same thing, T is temperature for Kelvin. Now, that's the first equation that you use. Second equation that you need to know is Ke as kinetic energy is equal to 3 over 2 kT. Now, one of the things about this is that the higher the temperature, the higher the kinetic energy. The lower the temperature, the lower the Ke. So Ke equals to 3 over 2 kT. Now, another important equation you have to know is that the internal energy U, okay, is equal to 3 over 2 NKT. But this form of the Ke is not, say, very widely used. We normally use this one, the nR delta T. This type is more normally used. So for change in U or change in internal energy, this is equated to be equals to 3 over 2 nR delta T. Okay. Now, so you have got these three equations. Please get to know them. Now, if you have got more bandwidth for more formulas, you could actually memorize this other equations on root mean square speed. This is the so-called the middle speed of the gas molecule, okay? And it's equal to square root 3 kT over m. So again, you can have some sensing of what happens when you increase the temperature. When you increase the temperature, okay, your speed root mean square value is going to increase, okay, and the relationship is square root, okay, from VRMS to square root of temperature, okay. So this is the link you can find, okay, between speed and temperature. Now we have got four basic thermodynamic processes or four heat processes, okay, that you have to know. Number one, isobaric. Now isobaric means same pressure. Iso means same, baric means pressure, so same pressure. So what it means is that this is a case whereby your pressure is constant, okay? Now, it could be that, okay, you've got container, then it's free to stretch or it move and responding to changes. So pressure is constant in that sense. Then what happens in that process of isobaric? Well, work done is equals to minus PdV. Okay, work on is minus PdV. And you have got heat to the system, Q. And then you realize just now that you have learned that delta U, which is change in internal energy, is equals to 3 over 2 nR delta T. So if I use the formula delta U equals to Q2 and work on, direct substitution will yield this. Delta U equals to Q minus P delta volume. This. Now, the second process is isochoric. Okay, this means same volume. Now, where volume is constant, this means that your system is placed into this, maybe this incompressible container, okay, and that the volume cannot change. So your volume basically can't change. And basically, if I have got a PV diagram, it will mean then that the PV diagram, I would have this as my graph. So it's a vertical graph in a PV diagram. And going back to isobaric, it will probably mean the PV diagram, okay, my graph would look like this. Same pressure. So this case isobaric, this second case is isochoric, where the volume is constant. Okay. Now, continuing, because your volume is constant, an interesting thing that happens is that you don't have delta volume. And because you don't have delta volume, remember that W is equals PdV, your dV is 0, so W is actually equal to 0. Okay. So remember that for isochoric, your work done is 0. And then when you put that into your equation of delta U, so delta U is equals to Q2 and work on is 0, therefore delta U is equals to Q. So for this specific situation, whatever energy you put into the system, Q, you directly affect the internal energy. So this is an important point to Take note. Now, for isothermal, now this is your favorite Boyle's law equation where your temperature is constant, iso same, thermal means temperature, so this means same temperature. So you, for this kind of graph, you actually have the usual Boyle's law graph where your P and V is inversely proportional to one another. You have got this kind of graph, okay? So it's a reciprocal graph, and basically this obeys the equation P1 V1 equals to P2 V2. Okay, I'll just write it down. Okay, basically P1 V1 equals to P2 V2. And for the lack of space, I'll just use constant, okay, to denote this type of graph. So when we have got this kind of isothermal condition, same temperature condition, you realize that the change in internal energy is zero. Remember that we mentioned that just now, if delta T is zero, okay, if this guy is zero, delta T is zero, my change in internal energy must be also equal to zero. So if my delta U is zero by definition, so if I sub into the delta U equals Q2 and work on equation, my Q is equal to minus work on. So all my energy supply, Q, goes to the work on of the system. So all the heat supply is used to do work only. Now, for the last processes called adiabatic, that means there's no heat exchange. It's very fast. Okay, the change occurs very, very fast. Okay, so it's like, for example, if you've got an insecticide, the container, suddenly you poke through a hole, the condition of the gas escaping is so fast, your insecticide container feels cool to the touch. Actually, it's quite interesting to have that kind of experience. Okay, sensation is quite cool. Yeah, anyway, so for that fast process, again, what you have is that your Q is very, very small. In fact, it's zero by definition because it occurs very, very quickly. So your Q is zero by definition. Okay. So when you input Q equal to zero, by definition, your delta U is equals to work. Okay. So all the work done is done to increase the internal energy U. Now you realize that for this isochoric, the energy you put into the system goes to change the internal energy. So U equals delta U. So Q go in, it will affect the change in internal energy directly. But for this adiabatic, any change in internal energy is used to do work. Okay, they are not the same arrow direction. So I want to repeat here for isochoric, any Q you put in affects the delta U, and for adiabatic, any change in delta U is used to be done work on. Okay, so for this isotherm, I need to also make mention that the product of the PV coordinates is the same. So what I actually mean is this. So let's say, for example, if I have got a, let's say, PV diagram here, hold on, and my curve looks like that. If let's say my first coordinate, and let's say this is 2, and let's say this is 4, and my coordinates will look like this, let's say 2, 4. Now, because P1 V1 is going to be the same as P2 V2 for Boyle's law, so it moving to a second pair of coordinate, and all this takes place in a constant temperature isotherm. So your Boyle's law, let's say if they ask you, okay, let's say if I know my volume here to be, let's say 5, and what is my pressure number here? So basically, you just have to use the product. Hold on. Yeah, so you just have to use the product of the first initial condition whereby your coordinate was first at 2 and your pressure at 4. So your product of this would be then equal to 8. So using that, this product must be also the same as the second set of coordinates. So 5 times this question mark must be equals to 8 as well, because the P1 V1 for first condition is 8 and P2 V2 being 8 as well. So necessarily then this question mark will have, it would be very easily worked out to be at least or equal to 8 upon 5. Because 5 times 8 over 5 will give you 8. So straight away from using this product, okay, of the first set must be equal to the product of the second set, I can easily deduce one of the unknown variables. Okay, this is just a specific note on this isotherms. Now, for the next process of adiabatic, now adiabatic follows this formula PV gamma equals the constant K. This gamma is really just the ratio of the specific capacity. So it's defined that this gamma is equal to Cp over Cv. Now, if you work the work done for this adiabatic, okay, so you actually work from PV gamma to K, then you know that W is equal to PdV, you use that, and it becomes W equals to K integral of dV over V gamma. Now, when you work from the limits between VI, volume initial, to V final, it will end up as W equals to K over 1 minus gamma, VF 1 minus gamma minus V initial 1 minus gamma. So this will be my work done equation for the adiabatic. Now, this is sometimes this kind of questions will come one or two in SJPO. Okay, this is for specific adiabatic processes. Okay. So we have got the first question to try. We've got this cylinder with the gas fitted with a piston. Okay, the weights are actually placed on top of this piston, so the gas doesn't go out. So for this kind of system, you know the number of moles are basically kept constant, and you don't have anything. Okay, so what happens that here? Okay, determine the temperature in which this gas must be raised in order that the height, okay, is increased. So I've got a raise in height. So I've got a raise in volume. Okay. Then what happened is that then they ask you for temperature. So temperature must change. So basically I have got a relationship that equates basically PV and RT. Okay. So it's also probably an isobaric situation. We can use that to start. So yes, so I was saying that okay, PV is equal to nRT. So obviously for the volume to be doubled, okay, it's raised. So you'll find that when you equate your temperature and the volume, when volume is double, your temperature is also double. But take note that for this temperature in degrees Celsius, you have to add the 273 to it. When you times 2 in Kelvin, it becomes 600 Kelvin. And then you convert back by deducting 273, you get 327 degrees Celsius. Please take note that for all thermodynamic equations, the temperature is in the Kelvin. Okay, for this question number 2, you realize that this ideal gas is heated. Okay, and this ideal gas is inside incompressible container. There's a keyword, incompressible. Incompressible just means delta volume equals to 0. And because delta volume equals to 0, it relates to work done being 0 because the work done is PdV or P delta V. So you can also know that your W is equals to 0 as well. Now, these are all clues to how you will draw your graph later, okay? Now then, I've got a second case. A balloon bursting and it causes the gas inside to expand suddenly. Again, this is another keyword. This must then mean it's adiabatic. Now, adiabatic means your Q equal to 0. Okay? And hence, like I mentioned, because your first part, your container is incompressible, so delta V equals 0, it must go to a straight line. And if it goes through a straight line, it's an isochoric process, okay? And since delta U equals to Q2 and work on, if my work on is 0, delta U equals to Q, so directly, okay, whatever energy you put in, okay, your U increases, okay? So this is the first vertical graph that you have. Now, for the second, because it's adiabatic, your Q equals to 0, okay, your delta U is equal to work done. Okay, so you realize that here, okay, this expansion means that then this will drop down an exponential graph, a sudden decrease, okay, and you have got this. So this decrease in internal energy, okay, will give you the work done. Now, this work done is expressed in the volume expansion, but it's really a reduction, a decrease in your internal energy. Okay, that's about it. Yeah. Now, this is a very fascinating question because it involves gas cycles. Now, basically, I've got a very complete diagram of PV processes, and it ends up in cyclic order. And for this case, you see that the arrow is in one complete order: A to B, B to C, C to D, and back to D to A. Now, this is anti-clockwise. Now, it could also be that some PV diagrams actually go around in a clockwise direction. Okay, these are very useful heat processors because it's used in engines of cars, in the aeroplanes and all that. Okay, because basically the piston goes through a series of compression and expansion, and it does very useful work to propel the object ahead. So let's start this question. So I have got from point A to point B. You can realize that, okay, I've got this processor starting from point A at 400 Kelvin all the way to point B, 720 Kelvin, point B to C, 380 Kelvin, and C to D, 200 Kelvin, and then back forth again to A. You realize that all 4 points are at different temperature. Now, then you're given this table from A to B, B to C, C to D, and D to A. And I've got this table in terms of increase in internal energy, heat supply, and work done. So first thing in your mind is that you have to put in the formula of delta U equals to Q2 and work on. Let's see if I can do that or not. Okay, so I will just do this. Delta U, check. So this is really a column of delta U. So I split it up. And this is equals to heat energy Q to the system. And then plus work on. Now, sometimes the table is in work by, then you have to go and change it to minus work by because work on is equal to minus work by, okay? Now, having said that, let's see. Okay, A to B, going from A to B, 2004 joules. So this left-hand side must be equal to right-hand side, given that this is 0. So this must be 2004 because 2004 equals to 0 plus 2004. So very easy. Next, from B to C, this is the isochoric, okay, isovolume case. So if my volume is constant, and because work is P delta V, my work done must be 0. So this work done is 0. And minus 2007 equating to the right side, this again must be minus 2007. Now, from C to D, this goes through an expansion. Okay, so you realize that here, your change in internal energy is minus 1002 and your heat supply is 0. So left hand side equals right hand side. Again, this must be minus 1002. Not a problem. Okay, pardon me. Okay, for this handwriting. Now, when you come back to D to A, this completes the entire anti-clockwise cycle. Okay, now there is this thing about the entire cycle in that the delta U for the entire cycle is 0. Okay, this is delta U of the whole system must be equal to 0. So what happens is that I actually have to sum up all this and then equate a number to make it 0. So let's see. So 2004 minus 2007 is about minus 300. Minus 300, add another negative minus 1002. That will be ending up as minus 1005. Oh no. Now this is minus 1005. Okay. Uh, okay, let me erase that and make it better for now. It's quite ugly. So minus 1005. It's quite a pain. Now, to add to this minus 1005 to make it 0, this D to A must increase in internal energy of 1005, positive. Okay, now, so D to A, this must be 1005 to minus away the negative 1005 before to make it 0. So this is 1005. Now, similarly, D to A, okay, is again isochoric, which is same volume. And with same volume, your work done is 0. So this is 0. And then this must be 1005. Okay. Now, meaning to say from D to A, if I want to put this information in, minus 1005 means that here I inject heat to the system. Okay. My Q that I injected is 1500 joules of heat energy. Just to make some sense of the numbers in the table. And when you look at it, you realize that from B to C, this part, I'm extracting minus 2100 joules. So I'm actually extracting minus 2700. Okay, you realize that how they extract the heat energy out from B to C, they decrease the temperature. C 720 to 380, heat is extracted by means of temperature. So my heat extracted is minus 2007. So the entire cycle seems reasonable. Okay, beautiful. Yeah, this is about it.